Wi-Fi acts as a bridge between the digital world and the physical air around us. It converts binary code, the ones and zeros of your data, into electromagnetic signals. These signals travel through the air as radio frequency waves, carrying your information at the speed of light. By manipulating these waves, Wi-Fi allows us to share vast amounts of information without a single physical cable. To transmit data, your device uses a process called modulation. This involves converting digital bits into analog radio waves. The digital bit stream enters a component called the modulator. The modulator changes characteristics of a radio wave, like its frequency or amplitude, to represent digital bits so the router can decode them. By observing these changes, the receiving device can reconstruct the original sequence of ones and zeros. Think of Wi-Fi frequencies like different radio stations. Every band serves a specific purpose in your home network. The 2.4 gigahertz band uses longer waves, allowing signals to travel further and penetrate through walls. The 5 gigahertz band provides much higher speeds, though it covers a shorter distance than 2.4. The newer 6 and 7 gigahertz bands offer massive capacity and extremely low latency, perfect for modern data-heavy applications. By managing these different bands, modern Wi-Fi ensures every device gets the right signal for its needs. In older Wi-Fi standards, the router could only communicate with one device at a time. This created a queue, similar to a single-lane road where traffic must move in a strict line. OFDMA changes this by treating the wireless channel like a multi-lane highway. The router divides the channel into smaller subcarriers called resource units. By allocating these resource units, the router acts as an intelligent traffic controller. It can send and receive data from multiple devices simultaneously, significantly reducing latency and congestion. Quadrature amplitude modulation, or QAM, is the secret to packing more data into every radio wave. It works by manipulating both the amplitude and the phase of a signal simultaneously. Think of QAM as a grid of coordinates. Each dot represents a specific combination of amplitude and phase that corresponds to a binary pattern. As we move to 4K QAM, used in modern Wi-Fi 7, we pack a much denser grid. This allows the system to represent 12 bits of data in a single symbol, dramatically increasing the total throughput. By packing more data into every wave, Wi-Fi 7 achieves speeds previously impossible, turning our wireless channels into high-capacity digital highways. MIMO, or multiple input, multiple output, is a core technology for modern Wi-Fi networks. Instead of a single antenna, MIMO utilizes arrays on both the router and your device. This enables the transmission of multiple, simultaneous data streams over the same radio frequency. By sending unique data on each spatial stream, we multiply the network throughput without needing extra bandwidth. This spatial efficiency allows devices to receive significantly more data in less time. Ultimately, MIMO transforms how we consume data, enabling stable, high-speed connections even in environments with multiple active users. As of July 2026, Wi-Fi 7 has become the gold standard for wireless connectivity. It has officially replaced older protocols to handle massive data loads efficiently. By providing unprecedented throughput, Wi-Fi 7 enables high-bandwidth technologies like 8K streaming and immersive extended reality to function perfectly over wireless networks. Wi-Fi 7 is the vital backbone for our modern high-capacity wireless demand. Multi-link operation, or MLO, is the defining breakthrough of Wi-Fi 7. It enables a device to connect to the 5 GHz and 6 GHz bands simultaneously. This creates a redundant connection, ensuring that if one band encounters interference, data flows seamlessly through the other. MLO effectively prevents data drops, making wireless connections as reliable as a physical cable. A wide Wi-Fi channel acts like a multi-lane highway for data. However, interference often blocks a portion of this road. Traditionally, interference would force the entire channel to slow down or even drop the connection. Preamble puncturing allows the router to carve out the blocked slice. It continues to send data through the remaining clean segments. By ignoring the noise and using the available bandwidth, we maintain high throughput despite local interference. Think of Wi-Fi channel bandwidth as the width of a highway. The wider the road, the more data can travel at once. In previous generations, like Wi-Fi 6, the maximum channel width was 160 megahertz. Wi-Fi 7 doubles this capacity to 320 megahertz. By expanding the lane width, we allow significantly more data to move simultaneously. This expansion is essential for demanding applications like high-definition 8K streaming and immersive extended reality, ensuring that the connection stays fast, even under heavy load. Doubling the highway width effectively removes the bottleneck, creating a high-speed lane for massive data throughput. Wi-Fi signals are now being used for much more than just data transmission. By analyzing the way radio signals bounce off objects in a room, modern routers can sense motion, posture, and even subtle movements like breathing. This technique relies on channel state information. When a person moves, they disturb the Wi-Fi field, causing predictable phase shifts and signal reflections. Modern enterprise Wi-Fi networks are constantly managed by cloud-based AI. This intelligent brain acts as a central observer, continuously monitoring every access point in the building. The AI analyzes signal reflection and device demand, predicting potential congestion before it happens. It can identify bottlenecks where traffic is beginning to slow down. Once a bottleneck is predicted, the system autonomously adjusts power levels and reassigns frequency channels. It clears the path, ensuring the data highway remains open. This predictive capability turns Wi-Fi from a reactive system into a proactive one, maintaining stable, high-speed performance without manual interference. The modern Wi-Fi industry has undergone a crucial shift. For years, the goal was raw speed, pushing bits through the air as fast as possible. However, raw speed is often unreliable, leading to jittery connections and dropped packets. In 2026, the focus is now on deterministic latency. This ensures that data arrives at precise, predictable intervals, mirroring the reliability of a physical Ethernet cable. By prioritizing stable timing over bursts of speed, Wi-Fi 7 provides the deterministic performance required for real-time applications like robotics and remote surgery. This evolution from pure speed to deterministic reliability is what makes current Wi-Fi the backbone of today's hyperconnected industrial landscape. Industrial automation is undergoing a massive shift. Factories are replacing rigid physical cables with the high-performance capabilities of Wi-Fi 7. With sub-5 millisecond latency, Wi-Fi 7 synchronizes robotic arms in real time, enabling seamless coordination across the assembly line. This connectivity supports digital twin monitoring, allowing systems to stream vast amounts of sensor data to virtual models for instant analysis. By achieving reliability comparable to a physical wire, Wi-Fi 7 transforms the factory floor into a flexible, data-driven environment. In crowded venues like stadiums or airports, older Wi-Fi networks often struggle with extreme congestion, leading to a phenomenon known as the stadium crawl. Wi-Fi 7 revolutionizes this experience by tripling the user density capacity. Through advanced OFDMA and improved spatial multiplexing, it effectively clears the bottleneck, ensuring data loads instantly even in the busiest environments. This upgrade eliminates the frustration of stalled connections, making high-speed connectivity reliable, no matter how many people are using the network. The long-standing debate between Wi-Fi and cellular networks is over. Today, technology focuses on convergence. Modern devices are designed to maintain simultaneous awareness of both local Wi-Fi and wide-area cellular networks. Through seamless handover protocols, devices transition between networks without the user ever noticing a drop in service. This ensures that your data is always delivered over the most efficient medium available, providing true always-on connectivity. By mid-2026, Wi-Fi has evolved into the primary backbone of the Internet. It carries over 75% of all wireless data traffic globally. This represents significantly more traffic than all cellular networks combined, proving that Wi-Fi is the core engine of modern connectivity. From homes to industrial centers, Wi-Fi enables the seamless data flow required for our global digital infrastructure. Wi-Fi operates on a shared medium, which means multiple networks are constantly competing for the same airwaves. Interference is inevitable. To manage this, routers use a listen-before-talk protocol. Before sending data, the router monitors the channel for existing signals. If the router detects a signal from a neighbor, it waits. It avoids crashing into existing transmissions, which preserves network integrity. Once the air is clear, the router begins transmitting its own data packets efficiently. Current Wi-Fi bands like 2.4, 5, and 6 GHz are becoming increasingly crowded as more devices join our networks. To solve this, the industry is pushing for universal access to the 7 GHz spectrum. This expansion acts as a vital upgrade for global connectivity. Opening this spectrum provides the breathing room necessary to maintain high performance and low latency in our most dense areas. By adding these new channels, we ensure that our infrastructure can support the next generation of high bandwidth wireless applications. Think of modern Wi-Fi not as a single radio signal, but as a dynamic, multi-layered expressway. Unlike older versions, this system uses multiple lanes simultaneously to maximize throughput. AI-driven management builds detours around traffic and interference in real time. The result is a connection that delivers data with the reliability of a wired cable. Wi-Fi technology has evolved from simple wireless internet to a complex, AI-managed infrastructure. This infrastructure now supports everything from global enterprise manufacturing to your home's streaming needs, ensuring connectivity is more reliable and intelligent than ever before. Our journey through modern Wi-Fi technology reveals a powerful, interconnected ecosystem. It is built upon four critical pillars that define the current standard. Advanced modulation and ultra-wide channels provide the raw throughput required for high-bandwidth applications like 8K streaming and immersive reality. AI-driven optimization and deterministic latency ensure that this speed is stable, reliable, and responsive enough for industrial-grade automation. Together, these advancements transform the airwaves into a high-precision backbone for our digital lives, pushing the boundaries of connectivity.